So dispersion model is generally used to predict mixing in the plug flow reactor. So what is a type of a mixing? So if you see the plug flow reactor, so plug flow reactor will design based on the assumption of all the element of fluid will have a same residence time. Same residence time means all the molecules are moving with the same velocity. So there is no question of getting mixed or collide. So are mixing with the other layer. So therefore, if it is not happening, then you can see always a flat velocity profile. Flat velocity profile is only visible when all the element of a molecules will have a same residence time. There is no eddies, there is no back mixing, and mixing will be there only on an axis. No longitudinal mixing will take place. So if this assumption will be there, then will be called this as a plug flow reactor. If any molecule is coming here, I'll show here. Any molecule is here and any molecule is here. If you take any instant of time, after some time again, so these molecules are not overtaking, same, they will be moving with the same velocity, and first it will come out, and after this distance this will come out. So there is no mixing. Okay, you can see here. So these, this and this will not mix with the this and this, but mixing occur in that particular axis. It is possible. Only this mixing is possible, but mixing along the length of the path is not possible. If you are mixing along the length of the path, there is a violation of a plug flow condition. Suppose this molecule is get mixed with this, and this molecule is get mixed with this. The older molecule is coming this, and young molecule is going to the older. So therefore, this is a violation of a plug flow. Then if this is observed, then flat velocity profile, then these will be called a ideal plug flow. Okay. If anything which is not there, okay, which is not there means not ideal, so then it is called a dispersed plug flow. So what is happening is here, this will be, I'll show this okay, element will be then I can see here. So this is a dispersed, so therefore all the elements of molecules will be get disturbed. So therefore these, okay, you can see here, so this is a area of disturbance. So therefore this disturbance you need to predict. So therefore due to this disturbance, so due to this dispersion, what is the extent of mixing? So therefore in a plug flow, what is a basic assumption? We are assuming there is no mixing at all. So but in reality, suppose if you calculate a conversion by using an ideal plug flow reactor equation, so if the conversion is 99%, same reactor if you employ in an industry, they say no, what you are saying is not correct, but due to some variation we are getting only 96%. So therefore this 3% deviation from ideal to the reality is by dispersion. So therefore some mixing is happening. We should be able to predict this, what is the extent of mixing. If the extent of mixing is more, dispersion will be more. If the extent of mixing is less, dispersion is less. So therefore we want to know the mixing, where whether it is a 0, whether it is 1. So 0 means no mixing, 1 makes complete mixing, in between it is a type of a mixing which will occur. If this is observed, then it is called a dispersion plug flow. What is dispersion plug flow? Opposite of plug flow. Fluctuations will be there due to diffusion and change in flow velocities, and due to the molecular and turbulent diffusion. So there will be a diffusion, there is a mixing, there is a eddies, and there is a varying velocities. But here there is no eddies, there is no diffusion, there is no varying velocities. So if it is okay there, then it is called a dispersed plug flow. This is a plug flow, this is a dispersed plug flow. I hope you understood why you want to predict. We want to predict what is the mixing condition in the plug flow. If at all it is there, then you should be able to predict this mixing by use of a dispersion model. This model is used to predict deviation of a plug flow reactor. This is a single parameter model, means we are going to develop only one parameter from which you should be able to tell about what is the extent of this dispersion. Therefore, it is called a single parameter model, often used to predict behavior of a tubular or plug flow reactor. So why it is used? It is used to predict what is the behavior, whether there is no mixing or mixing, what is the extent of mixing. Okay, consider a plug flow of a fluid on top of which is superimposed. Superimposed means some other molecules will also be coming up. So there is a layer. So superimposed means you can see backside what is happening. So up, okay, you can easily see if you cover, so you can easily see what is happening behind. That is superimposition. Okay, consider plug flow of a fluid on top of which is superimposed some degree of back mixing and intermixing, the magnitude of which is independent of the position. Suppose some mixing is here, then again some mixing will be here, some mixing will be here. So therefore, these magnitude will be independent. Here the mixing is more, here the mixing is less, here the mixing is reduced. So therefore, but mixing is there. So therefore, this magnitude of mixing is independent of their position. So therefore, that time we should be able to predict what is the extent of mixing. Therefore, no stagnant regions, okay, independent of the position within the well. Therefore, no stagnant region, no bypassing or short circuiting of the fluid in the vessel. This is called a dispersion model. Okay. So therefore, ideal plug flow, you will assume a small, okay, change. That change we are going to use, okay, predict by the dispersion model. In plug flow, we will be assuming there is no mixing, there is no eddies, there is no varying velocities. Okay, this is a okay model which is called a dispersion plug flow model, which is used to predict the extent of mixing in the plug flow. Okay, I hope you understood the concepts. Any confusion over here? Very simple. This is used to predict what is the extent of mixing in a plug flow. That's it. Okay. So now, same thing. Okay, we'll be discussing. Since mixing process involve, what is a mixing? Mixing means it is a intermixing or molecular mixing, and it is along the flow path, or it is axial and longitudinal mixing. It may be shuffling or redistribution of the molecule either by slippage or eddies, and this is repeated many times during the flow of fluid. Okay, so it will be like this. Suppose if this is a plug flow, this is molecules, first molecule, and this is a second batch molecule. So these will start mixing. So this will be coming back and mixes. So therefore it is along the axis. Eddies will generally, okay, mixing, complete mixing, so which will be occurring in the entrance and okay, exit. So therefore these are the main cause for the mixing. So therefore it is always there in a open vessel. We have open vessel means there is a mixing in a entrance and exit. Okay, if there is no mixing in a entrance and exit, then you will be having a closed vessel. Okay, it is by slippage, eddies. This is repeated many times, here many times. Okay, these disturbance to be statical in nature. So therefore, for our information, what we do, so rest of the disturbance will be not taking. We will be taking only the disturbance where we want to model. So only this point we are modeling. So only, so this is a disturbance. We can take this as delta x. What is the amount of disturbance? Delta x. Remaining is statical in nature. We are assuming the same disturbance can be seen here. So this will be again different type. So therefore, but we want to predict what is the extent of mixing in this region. So that will be applied to the entire range later. Okay. We can consider these disturbance to be a statical in nature, uh, somewhat as a molecular diffusion. Therefore, we can use a similar to the fixed law of diffusion for the transport of a material in axial direction. So therefore, mixing will always happening along the length of a reactor. So therefore, here the mixing will be on the axis, which will be taken as a fixed law of a diffusion for the transport of material. Same equation we'll be using to develop the reaction, because the molecules will diffuse due to the mixing, or it is usually due to the change in concentration, higher concentration to the lower concentration region. But here we are not taking any reaction. Only we are assuming water is flowing through the reactor. So therefore, whatever the transport of these molecules will be somewhat like a molecular diffusion. When you use a molecular diffusion, I can easily use a fixed law of diffusion to describe this model or to develop this model. So therefore, we'll be writing a material balance. You have to practice this. Definitely, this question will be there. Explain dispersion model and what is the dispersion number, why it is used. Okay. So now you take a material balance. So before taking a material balance, I'll show this diagram how to take a material balance. So you can write the reactor and see. So this disturbance I am taking into account. So this is a PFR. So at that particular point, I am accounting how much variation is there. So total length is 0. X is equal to 0 means it is inlet. X is equal to L is outlet. If you take this total length, it is a total length of the reactor, means these molecules have to spend L time to come out from the reactor. So therefore some material will be entering. You can look at it. Some material will be entering and this material has to be lived. And so mixing means something is not coming in time. It is accumulated. Okay, see here. So this is accumulation because here it is again coming back, then again it is coming back, again it is coming back. So therefore, due to which, so this delta X accumulation will be there. Getting understood? Very simple. R is a radius of a reactor. But this material balance equation you have to remember. So therefore, this disturbance from inlet is X. Suppose if you see delta X, so from the length, this is a length. From this, the length of this disturbance is occurring at a distance of X at X, and this disturbance is magnitude of this disturbance is delta X. So therefore, as I told, moles of in only it is in, and what is out? Something is accumulated and something is out. So therefore out plus accumulation. So therefore you can see here minus d dc by dx. So therefore this is a fixed law of diffusion. Okay, this is by diffusion. UC, it is material transported through the convective flow. So UC is a convective flow. U is a velocity, C is a concentration, UC is a convective flow. It is length pi r square, and how much time it will be taking? Delta t, delta t. Okay, so this is in. What is out? Minus d. So see here, it is entering at x. You can see here, it is entering at x. Okay, up to here it is x. Okay, material is coming here and it is coming. If you write here x, okay, what is coming out? It is x is already there. How much it is taking? Delta x. Correct na? Up to here it is x. Definitely this x should go in. Something is come out through this. So therefore we are accounting this diffusion. So therefore x plus delta x. So therefore same. If you see the material movement is always the fixed law of diffusion plus convective flow. So therefore minus d dc by dx plus uc. Here it is x. You can see here. At out it is coming by x plus delta x. We are not taking to the entire account. Only how much material is entering, how much material is leaving. It is same as in is equal to out. Okay. So pi r square delta t. So pi r square delta t. Okay. So what is the accumulation? Accumulation is only along the area. So therefore this is surface pi r square. Okay, pi r square. How much concentration delta t is associated? Delta x is associated delta c. Okay. So where it is associated? In delta x. So there is no time because accumulation is the known amount, known magnitude. So therefore pi r square delta c delta x. This is time, delta t is time taken or at that particular time it is entering. So that is delta t. So from here to here it is delta t. So if it is delta c, delta x, and I can take this as delta t. So everything, okay. It is the amount of concentration, magnitude of a concentration to pass delta x is delta c. Amount of time it is taken to pass delta x is delta t. So therefore I am multiplying delta t for all the component you can see here. So here what is accumulating? Accumulating something which is related to the concentration. So therefore delta c. So where it is accumulating? In delta x. Pi r square delta c delta x. I hope you understood this derivation. Okay, you write down. So minus d dc by dx is what? Quantity of material moving by axial dispersion. This is a dispersion equation. So what is UC? Quantity of material moving by axial, moving by convection. UC is called convective flow. So it is by the convection. D is diffusion coefficient. U is velocity of a fluid. C is a concentration of a fluid. So please all of you write. So if you have any questions, any doubt in understanding the derivation, please stop and ask me. That I'll, okay. So after that, what we are doing, we are dividing our equation by pi r square delta t delta x. If you okay rewrite it, so it will be d dc by dx of x minus d dc by dx x plus delta x divided by delta x minus uc of x minus uc of x plus delta x by delta x is equal to dou c by dou t. It is dou t, dou c by dou t. So you have to remember this step, okay? You have to remember this step. This is in minus out, in out, in out. Okay, like this. This is in out, in out. So therefore, you will be multiplying this term here. 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 So therefore, when you do in minus out, see here. So in minus out, in minus out. Okay. So therefore, you have to write one more step. Okay. X in. So for diffusion, it is in. Diffusion, it is out. Convective flow, it is in. Convective flow, it is out. So how it is written? Okay. So this and this will be combined. So it will be taking here. UC will be taking here. So therefore, d dc by dx in d dc by dx x plus delta x. UC at x, UC x plus delta x. Same thing. It is rearranged. At the end is equal to delta c by delta t. Don't get confused. Very easy. Actually, you'll get minus here. Here it is plus. So therefore, okay, it is plus and minus. Here plus and it is minus, minus and minus. If you want to write, you write it. Shall I go to the next slide?
Yes, sir.
Okay. As limit delta x and delta t tends to 0, means there is it becomes very negligible as compared to length of reactor. Means what? Why will tends to make it 0? So actually in your mathematics also we'll consider. So if you compare the length and this is what I'm mixing, so therefore it is negligible. So therefore it is very small as compared to the total system. Okay. So therefore this is very small. Therefore as it tends to 0, above equation can be written as directly. You should remember this. Don't worry about the mathematics in detail. You can, I'll explain, but it is d dou c by dou x. So second order dou square c dou x square. Here also dou c by dou x. See here dou c by dou x, dou c by dou x, dou c by dou t. So here d u. So this is only the dispersion model. Okay. we'll solve this further. Okay, here it is dc. It is a differential form. Therefore, 2dc. Therefore, dc square by dx already differential form. This is not in a differential form. So therefore, I can write dou c by dou x. Okay. So therefore, if there are two differential terms, dou c square by dou x square. Here there is no differential term. If you okay, so differentiate, it is half. If you differentiate, it is half of it. So therefore, dou c by dou x. Okay, it will be like this. Dou c by dou x is equal to dou c by dou t. I want to write in a differential form. So this we can write our equation in a dimensional number, but this will not give any information. You cannot understand anything from it. So only you can see the constant diffusion coefficient and velocity, concentration, time, and that's it. Okay, there is no. But we can write this equation in the dimensionless form. So therefore, you try to convert this into dimensionless form. So I'll write z. So what is t? T is a time. I want to write z as a time. See here, what is dimensionless? Something you divide with the same dimension, both the units will be get cancelled, so you will get a dimensional. So therefore, z is, I write it is a measure of time, but it should be second or minute or hour, anything, correct? So time. So therefore, how I'll do it? Suppose z is t time is in second. So I should get cancel both the unit. So therefore, I'll divide by this mean of a t bar. So mean is also second, get cancels. So therefore, z is equal to t by t bar or something x and l. Okay, z is if it is okay time. So here it is length. Sorry, z is in length. I have shown the time, right? If it is theta, okay, time is theta, t by t bar. I'll show. I'll explain. Okay, so therefore z. What is z? Z is length. Length is in meter. X is in what? X is also in meter. L is also meter. So therefore I can write this as x by L. Don't see this one. X by L. So therefore x is equal to ZL, not Z plus L. It is ZL. Okay. X is equal to Z into L. It is into L. Into L. So theta. So therefore it is also meter. It is also meter. Get cancels. You will get a dimensionless length. So theta is dimensionless time. So therefore T by T bar. So therefore theta is equal to tu by L. So therefore I can write theta is equal to tu by L. So because t bar is equal to L by u. So t bar is length by velocity. So length is meter, u is velocity meter per second. Meter get cancels, again you will get s. So therefore theta is equal to tu by L. So t you can write, t is in second. You can see it. Velocity is meter per second. Length is in meter. So therefore t u by L theta. Okay, it is dimensionless because you can see here t is in second, u is in meter per second, L is in meter. Second, meter, meter. So therefore dimensional. Theta is equal to tu by L. But what is t bar? T bar is L by u. Therefore, I'll write t is equal to theta is equal to tu by L. T bar is what? L by u. So I am substituting t bar L by u. By u it will be co. So therefore you can see here x is equal to z into L, right? X is equal to z into L. X is equal to z into L. First you take it. X is equal to L into Z. Okay, L into Z. Okay. So therefore you take a reciprocal of it. You take a reciprocal of it, 1 by x. What you know? You know the length of your reactor. Therefore L cannot be changed because it is not varied, it is fixed. So because you are doing experiment in a a known quantity or a known material or known reactor, it is length of the reactor is known. So what is z 1 by z? So therefore x is changing. So x is varying from x is equal to 0 to x is equal to 1. L is fixed. Z is also time. So that is also varying. So therefore I can write this as it is varying with respect to concentration. So therefore what is important? We want to predict the concentration. Concentration is changing with respect to this. This is equal to 1 by L dou C by dou Z. I want to write with respect to concentration. So therefore, with the definite concentration, that particular concentration. So therefore, this equation is written by this x. Similarly, you can write x is equal to Lz, right? X is equal to Lz. So therefore, again, you second order differentiation. Dou square C by dou x square is what? Squaring 1 by L square. Dou square C by dou Z square. Same. It is directly from this square dou square C dou x square 1 by L square dou square C dou Z square, right? What you know. So second, theta is equal to tu by L. Okay, you can see here. So theta and t are changing. So therefore, I want write in terms of t. So therefore, I'll write t is equal to, I'll take L here, L theta by u. Okay, so this equation is required. Again, you reciprocal it. It is 1 by t is equal to u divided by L into theta. Velocity of the fluid, flowing fluid will be fixed, and then length is also fixed. What is changing? Dou t is changing with respect to dou c, and dou c is changing with respect to the time. So you can see a same equation. Can you get same equation? You get it. I hope you have cleared all your doubt. There is no confusion. Absolutely right. Now you substitute this value in above equation. You can see here what is there in above equation. Dou c by dou x square. You substitute the value of dou c by dou x square, dou c by dou t. Okay, I'll write it. What is dou c by dou x square? It is okay, d. It is already there. Okay, dou c by dou x square. D you have to write. Dou c by dou x square is dou square c by dou z square into L square. So therefore I am writing this. Okay, and then it is next term is u by L dou c by dou theta, then u by L dou c by dou theta. Second term is dou c by u by L dou c by dou theta. After writing this, multiply this equation by L by u. So therefore I'll multiply it here. L by u, L by u, L by u. You can see here this will be get cancelled. This will be get cancelled. This, 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 this. Therefore, you will get d by ul. You will get take some other color. D by ul dou square c by dou z square minus dou c by dou z is equal to dou c by dou theta. This is what called a dispersion model. So therefore, what is a value you are looking for? This is the value you are looking for. D by UL. D by UL is a dispersion number. That's it. So that dispersion number will tell you about what is extent of dispersion. Hope you have written. We'll see. Next slide. So therefore, dou by UL, dou square C by dou Z square minus dou C by dou Z is equal to dou C by dou theta. This is called a dispersion. Where the dimensionless group D by UL is called a vessel dispersion number. So therefore, this D by UL is called vessel dispersion number. D by UL is called where the dimensionless group. So this is a dimensionless group. D by UL is called vessel dispersion number. We want this value only. So this will be help to solve the problem related to the mixing. Is the parameter which measures the extent of dispersion. D by UL is the parameter that measures the extent of mixing. Means what? If D by UL is equal to 0, negligible dispersion, hence the condition is plug flow. If d by ul is varying from 0 up to infinity, so if it is very large, then it is called a large dispersion. Hence, it is a mixed flow. So therefore, d by ul as tends to 0, then you can say there is no mixing. Then given condition is plug flow. If there is a mixing, you can account for that. If it is continuous, very large mixing, then it is called a mixed flow. So this is what definitely one question. Write a note on dispersion number or explain dispersion number. What is dispersion number? Explain and derive the equation for dispersion number. Is there any doubt regarding this derivation?
Sir,
Tell
sir,
me. Tell me.
sir, can we say practically it is a dimensionless length?
Louder,
Practically it
louder.
is possible.
Huh?
Sir, in this derivation, we have used that practical dimensionless length.
Oh, yes, tell me.
Sir, practically it is possible to say that.
That's why. So d by ul you will use in the practical only. So this we are going to calculate. We will conduct the experiment with the tracer. Okay, and then you will calculate the d by ul. So therefore, that will give whether mixing is there or not mixing. Suppose if you are using a dispersion, if you say there is no mixing, I'll conduct the experiment and I'll calculate d by ul. Then I'll calculate a. It is like NRE. So if NRE is 10,000, what you say? Turbulent. If NR is 2000, less than 2000 or 1200, what you say? Laminar. Same. So NRE you have derived, no? Same way. dv bar rho by mu, that is also dimensionless number. NRE is dimensionless number. NPR dimensionless number. Nusselt number is dimensionless number. Yes or no? Rushabh? Rushabh?
Yes, sir. Sir,
Tell me. You got your point?
yes, sir, I got, but while deriving, it is theoretically possible, but practically it
No,
cannot.
NRE is also theoretical value only, no? NRE is also theoretical. So where you have conducted experiment, you have not conducted any experiment. This is only applied to the experiment. You have experiments and you are going to do that. So NRE is what? NRE is not experimented first. They have derived, no? Renard C has conducted the experiment and he developed a NRE related to the dispersion. related to nr is equal to d v bar rho by mu. So this is also derived. Huh?
Yes, sir.
Then where you got this Nusselt number? You write Nusselt number. Okay, who got this one Nusselt number? Then actually is here. Whatever the NR you calculate, no, if it is 10,000, okay, if it is 10,000, so actual there it will be not 10,000. Some variation will be there. So therefore we want to account the deviation. So the mixing is a big problem in a process industry in plug flow reactor. And then the complete mixing, if it is not possible, that is also a problem. So therefore some parameter models should be used. Okay, whatever the heat transfer coefficient you calculate Q theoretically, and go to the industry and check, that is always varying. If you calculate 5,000, they will say 4,600. Getting na? Theory is to understand how you are doing, what are the equations you are doing. But when you apply into the industry, definitely there is a deviation. You cannot get the same value. So therefore you should be able to predict why it is going wrong, what other things should be calculated. Even in thermometer measurement also, if you take a thermometer and measure 100, but look at the wrapper or whatever the cover or instruction manual, they will say it is plus or minus 0.05. Means what? What it mean? There is always a error means that is forced or unforced. Something will be there, but it is accurate. But if you want to do it, but this error should be accounted doing the large scale production. 0.05 means in your 1 liter, 0.05 is negligible. When he is doing a 10 lakh liter, 0.05 is important. Yes or no?
Yes, sir.
In your laboratory, you are handling a volume of 100 ml, 200 ml. But in industry, they will be handling in terms of a crore liter, 10 lakh liters. Getting so that 0.05 accounts a very, very big number. So in the industry, but we say this is very, very negligible. We can neglect in the classroom. So this is what. So therefore, so whatever the theory we learn, so D by UL, we should understand. This will give a information about whether mixing is happening or not. So if there is no mixing, definitely D by UL is equal to 0. If D by UL is a number, you will get some range. If it is a very large dispersion, large dispersion means you will get a value greater than 1. It is a large disturbance. If it is 0, it is. If any value, the range is between plug flow to mixed flow. Okay. Any other questions? We'll solve some problem. You'll understand. Okay. How to use it.
Okay, sir. Thank you.
We'll solve some problem. You will come to know how to use this. Okay. D by UL in your problem. Okay. If you have any questions, you can ask me.
Sir, please send this recorded video.
Yes. Yes.
Please send this recorded video, sir.
Yes. I'll send. But I have put the recorded video. Only 3 or 4 people will watch. Okay. See. Okay.
Sir, that 4 you have put.
Which one?
Remaining till today's class also you please put, sir.
Yes. I'll say. Okay.
Sir.
Okay.
Thank you, sir.
Okay. Please watch because you will not get
Yes,
all
sir.
this explanation in the book. So book
Yes, sir.
only this much is given. What I have written. Okay. So not only this, only the final equation is written. So therefore.
Yes, sir. So only we want it, sir.
Yes. Please see here, when you attend the class, you will understand the significance of each point, what is written in the book. If you think I can read and pass, passing is not a problem, scoring is not a problem. But you are missing what is important as an engineer, what industry want, and then how they will interpret. Just now, Rishabh asked, what is a theory and a practice? So you will understand by solving the problem. So definitely there is a deviation. So therefore, if you interact, if you listen to the classes, definitely you will understand more thing why we are using, how it is interpreted. Okay. So therefore, we are interpreting the particular equation in a particular form so that we can able to use that information to identify whether mixing is there. You see here, this equation is okay, not at all important. Only one number will represent this equation, d by UL. Only we are taking the d by UL. So only use that, you will get the information about the mixing. That's it. Okay. So we'll see remaining thing in the next class. We'll solve 1 or 2 problem so that you will be convenient. Up to here, you will get 1 question sure. Okay. So it is very easy chapter. You can score 20 out of 20. Okay. Okay. Thank you very much for attending today's class. If you have any doubt, still you can ask. Otherwise, I'll end the meeting. Okay. Thank you very much for attending today's class. Okay. I'll end the meeting. Thank you.
Thank you, sir.
Thank you. Thank you.